Okay, diving right into compression now. Let's take a look at these critical elements. So here are some test specimens of some tube columns. You can see this one's longer and it's bowed out and buckling. These ones are shorter and you can see there's local buckling. So as the member gets longer, it's more prone to a global failure, and as it's shorter, it's more prone to either a local buckling or even a pure yielding. Another photo here of a wide flange column. That thing's really going to work or getting worked over. And then a video here, you can follow the YouTube link right there. Okay, deformation of a column, as might assume if it's under compression, the material shortens, the circles become more oblong, but in the opposite direction of tension. Unlike the other modes we've talked about, columns really are fully driven by buckling. It's pretty rare that you'll have a column short enough and slender enough that it only fails in compression yielding. So we can have single curvature columns where it basically looks like a smile or a frown, however you look at it, or double curvature where it goes through a point of inflection and has two types of curving to it. This will actually carry more load than that if the lengths are the same. All right, P delta, so as the column deflects globally, you can have an increased moment in the column, and then locally between points of inflection, you can have an increased moment in the column. Sometimes we need to consider this, sometimes it's built into the equations. I'll let you read the residual stress section here and just jump into K factors, which really relate a pin-pinned situation, which I don't have one there. So let's say I have a pin here, or where do I have one? Right here, pin. So 1.0 is the K factor. If it's fixed pinned, it's going to be less, so it's going to behave like the column shorter. If it's fully fixed, I'm going to be 0.65. I haven't given you the theoretical values just because they really aren't relevant to the discussion. All right, so one of the things we need to understand is the type. So this is kind of the simplistic version of K factors. We have a more complex version depending on the frame type, so sway versus non-sway. And really it comes down to, are we looking at moment frames or brace frames? So in this moment frame, you can get quite a bit of lateral movement, whereas a brace frame like this, even if it was a tall building or taller building, the braces are quite stiff and limit the lateral movement. So if we want to find the K factor, imagine this is our column between point B and point A. This nomograph method looks at the stiffness of the beams and the columns coming into the joints, and then we decide or we develop our K factor from that. So let's say our stiffness of our beams and columns coming into this joint is pretty flexible, so close to infinity. But then on the other side, it's very fixed, very rigid, so maybe it's 0.1. And I would draw a line here between those, and my K factor would be 0.73. Usually, we're closer to a relationship like that, or something that would push our factors down, maybe even something as low as this. So in building frames, what we're doing when we go from these simple analogies to these nomographs is we're taking into account the reality that this frame or this column's fixity at each end is a function of the beams and columns coming into it at each end. All right, same thing for a sway frame. The difference you can see is the K starts at 1 and goes to infinity, whereas the previous slide started at 0.5 and went to 1. So moment frames can be a lot more sensitive to lateral deflection, so we need to take that into account when we're calculating the K factors. Okay, so the basic strength equation for a non-slender symmetrical column is the axial load or capacity is equal to critical buckling stress times the gross area. 0.9 is the phi factor that we need to apply to that. So for inelastic buckling, so if our slenderness ratio is less than this value, so we calc LC over R. LC would be the length of the column divided by the least radius of gyration, usually R sub y. If that's less than this equation, then we can use this critical stress equation here. And then this F sub E is really an Euler buckling equation. It should look somewhat familiar to your strength of materials book. So FCR plugs into right here in this equation. If our column is in the elastic buckling range, then we're going to use the 0.87 times the critical buckling stress. So we start by calculating this term, decide which equation to use, find the number, and then plug it back into here. Okay, so you can see here for different slenderness ratios, we have the Euler buckling curve, we have 50 KSI and 36 KSI material. So if we just stayed with Euler, we would say, well, we have an infinite amount of strength when we get to a low buckling ratio. But realistically, the actual member stress, the strength of the material itself, takes over. So we need to think about that. Okay, this table is pretty handy if we don't have a table directly for our column. We can come in here, let's say we have a slenderness ratio of 146. So right here, and a yield strength, let's say it's tube, so 46 KSI can come over, and my critical buckling stress times phi is 10.6. And then all I need to do here is multiply that 10.6 kip per inches squared by area in inches squared, which gives me kips of column strength. You'll see here that for lower slendernesses, we are getting, we're basically 0.9 times 46. But as we get to very slender, say we're up to 200, we go from 41 kips per square inches to 5.5 plus kips per square inch. So at some point when we get to around 200 for a slenderness ratio, things just don't calc out so well. Okay, another great table from AISC are these strength tables. So let's say we have a W14 by 500 column, and I'm using LRFD, and I have a 22-foot unbraced length. So that would be L over R right there. So I come over, I've got 6,140 kips of capacity, which is huge. So that would be like a big commercial or industrial type building column where you need that much juice. The table also has some other helpful things that we can get into in class if you want to know more about how to use this table. All right, oftentimes we have combined axial force and flexural force, and we need to look at the combined effect of axial, flexural, and what it does in reality. So it may be this, if these were subtracted, maybe this line would shift over here to something like that. All right, the code gives us some simple equations, kind of an interaction type equations, where if our axial stress is over 0.2, the ratio, then we use this equation. We're basically taking the ratio of demand to capacity, adding them up. If it's less than 1, then we're okay. If we have low axial stress, then we have this different equation, and really it just boils down to what are the factors on things. But the bottom line is we're looking at ratios of demand and capacity for both axial force and moment. And the reason we can add them together is because the stresses add like they do right here. Okay, that's kind of the basic introduction to columns. As far as drawings go, here's an example with the columns called out in it. These type of braces actually can carry compressive loads as well, so both the columns and these braces will carry compression loads, and we would design them like columns. Here's a base plate of a pretty heavy column. So you can see in plan view quite a few anchors. This has a big shear lug because it has a heavy brace coming into it. Column splice, we're trying to mate the flanges together. And then here's a thermal column splice on kind of a funky project where above the roof there's this huge structure, and the owner wanted to limit the thermal conductivity into the structure from basically this thermal antenna. Okay, so that's that. We will talk more about this soon.